Thank you very much for your nice introduction, and without any further ado, let us move to the talk. I'm going to begin with a deliberately vague definition of orbitals, also some remarks on the notation, and that is followed by two reminders. So what is an orbital? An orbital is any function that depends on a position vector of a single electron in the Cartesian space, provided this function is continuous everywhere, is finite valued for all values of vector r, and also very often, and also is square integrable. Square integrability, of course, is needed for normalizability of the orbital, and very often additional condition is added, namely that the kinetic energy calculated with an orbital is finite, which means that the norm of a gradient is also square integrable. Now, in general, orbitals are complex valued. However, in the absence of magnetic fields, we can always work with real valued orbitals, and if there are any degeneracies which admit complex valuedness, we can always apply some unitary transformation which restores the real values of the orbitals. Now, I'm going to stay today within the realm of non-relativistic quantum mechanics, and that means that spin functions are well-defined functions. We have two spin functions, alpha and beta, for electron with a spin up and spin down. And if we multiply an orbital with one of those spin functions, we obtain something which is called spin orbital. A matter of notation, notation of n being a combined Cartesian and spin coordinates of nth particle is commonly used, and that's the reason I'm going also to employ it during this talk. So don't be surprised by some strange integrals which have d1, for example. This is nothing, we are not integrating over number 1, but we are integrating over vector r1 and summing over s1, two possible values. And just two things to remind mostly myself, that atomic units will be used throughout the talk. So h bar equals m equals e equals 1. And also from time to time, I will be mentioning something called two-electron harmonium atom. And this is nothing else but two electrons in a confining potential, which is harmonic instead of Coulombic. So we can imagine that system as two electrons on springs that repel each other Coulombically, but instead of being attracted to a nucleus Coulombically, they are attracted by harmonic potential. They are confined by the harmonic potential. I understand that we have chemists and physicists, and maybe some mathematicians, and maybe even some computer science in the audience, but I'm pretty sure that every single person in this room came across the concept of orbitals during some point of his or her education. I can see some people nodding, so I'm not mistaken here. And for me, this moment came during second year of secondary school in Poland, when I was asked to study this humbly looking book. Is in Polish, it says the structure of atom and chemical bonds. And if you open this book, you would see those familiar orbitals, s orbitals looking like balls, and p orbitals with lobes, and some leaf-looking d orbitals. One really went beyond that. And those are orbitals that chemists know, and apply very often, because there is a common belief within chemical community that with orbitals you can explain, and I'm exaggerating here a little bit, almost everything in chemistry. You can explain chemical properties, you can explain reactivity and so on. Of course, this is not true. So to message to students when your professors tell you that orbitals determine, so simple orbitals determine everything, don't believe them. Things are much more complicated than that. But anyway, all those pictorial representations of chemical bonding, orbitals, orbital energy diagrams, and so on, come from some mathematical background, and this formalist that is responsible for that is called LCAO, and is mostly it mostly came through the efforts of a single person, who is Robert Mulliken, whose efforts were acknowledged by fact that he received Nobel Prize for development of theory of chemical bonding. LCAO, linear combination of atomic orbitals. The very moment we say it, we run into trouble. Why? Because there are no atomic orbitals in molecules. There are no discernible atomic orbitals. How can you get atomic orbital in a molecule? So there is presumption that we are going to use some kind of atomic orbitals as basis functions. But then, what are those atomic orbitals? Are those hydrogenic orbitals may be corrected for some screening effects, or are those Hartree-Fock orbitals? It turns out that either choice is not particularly good if you want to get calculations that are capable of quantitative prediction of electronic properties that determine physical and chemical properties of atoms and molecules. You cannot use either set of orbitals. You have to use something better than that. Now, before telling you a little bit about different types of orbitals and their rigorous definitions, I'm going to digress for a moment and ponder the question whether orbitals are measurable quantities. Now, in physics, there is a concept of observables, and observable is a physical quantity that it can be calculated as an expectation value of some quantum mechanical operator, and orbitals obviously are not observables. There are no universal operators that are going to give you orbitals. But there is a somewhat broader concept, which is that of measurable quantities. Now, when we think about most of the measurements that are done in physics, nothing is really done directly. Now let us think, for example, about the determination of electron density, which is an observable. We cannot measure electron density directly. We, for example, can run an X-ray diffraction experiment, and in this experiment we are collecting intensities of diffraction in different directions. From there we try to recover the amplitudes, because obviously the phase information is missing. And also some people got Nobel Prize actually for figuring out how to get this missing phase information. And after quite a long process, and we do Fourier transform and so on, finally we have electron density. But one can ask in principle the following question: what is stopping us at electron density? Can we keep on performing some mathematical operations? Yeah, so not only we are recovering the phases from the measurement, but doing Fourier transform and so on, but what prohibits us from going further and from electron density, figuring out positions and nuclear charges of nuclei, and also from integration of density with no number of electrons, and that gives us electronic Hamiltonian, and that gives us wave function, and that gives us orbitals. Yeah, so are orbitals measurable quantities or not? Well, it's for you to answer according to your personal taste, so to speak. As I already said, there are different types of orbitals. They come in different flavors, and which type of orbitals one uses in a particular situation depends on what we are trying to accomplish. Here comes some more familiar case of orbitals, Hartree-Fock orbitals, which are defined as those orbitals that minimize electronic energy calculated with Slater determinant constructed from those orbitals. This energy called Hartree-Fock energy is never below the true energy, and usually is above. There is another set of orbitals which are called Kohn-Sham orbitals. Well, I think some physicists definitely heard about them. Yeah. Those orbitals minimize the energy expectation value of Kohn-Sham Hamiltonian, and in principle they are capable of giving us exact energy. But there is only a tricky point here. Nobody knows the Kohn-Sham Hamiltonian, which comes for a Kohn-Sham functional. So, sure, in principle you can get exact energy if you know the functional, so you know the Hamiltonian, but nobody knows how to calculate it, and I don't think the situation is going to be changed in near future. There are some other orbitals which are not based on energy criteria. For example, Brickner orbitals. Brickner orbitals which are defined as those that when you form a Slater determinant from them and you calculate the overlap with the exact wave function, that you maximize this overlap. They are used in quantum chemistry quite often. There are Dyson orbitals, which are generalized overlaps between the wave function of a given system and all the states, electronic states of a system which is ionized, which means has one less electron. So they are used for description of ionization processes. Now, there are natural spin orbitals I will be talking about very soon. There are some corresponding orbitals, maximum similarity orbitals, some localized orbitals afforded by different localization criteria, and there are also some ill-defined orbitals. And some chemists like them. So, for example, when we talk about natural bond orbitals, you see this little word bond spoils everything. Natural orbitals are well-defined, but natural bond orbitals are not. Now, to get some feeling what those orbitals do, let us look at one of the simplest systems that one can have is a system of 2 electrons in a singlet state, in a ground singlet state. And we are going to look at the spatial part of a wave function of that system. There is obvious spin function here for a system, for a singlet coupling of 2 electrons. We have a spatial part. And here, for the first time, we encounter natural orbitals. It turns out that the spatial part of this wave function is given by a spectral representation in which the eigenfunctions are those natural orbitals. Please pay attention to one fact. We have a single summation here. We are not having summation over n1 and n2 and orbitals index with n1 and n2. We have single summation, which means that this is the most compact representation of a wave function in terms of 1 electron quantities. And this property is not only a property that works in case of 2 electron systems, but also in a certain sense, which I don't have time to go into details right now, which also works in general systems for any number of electrons and not necessarily in singlet states. We have Hartree-Fock orbital, only one Hartree-Fock orbital, because 2 electrons is a solution of this nonlinear Hartree-Fock equation. We have occupied Kohn-Sham orbital, which is nothing but the square root of electron density per spin. Brickner orbital, which turns out to be the same as the first natural orbital if we order them according to non-ascending lambdas, and lambdas are called natural amplitudes. And we have Dyson orbitals. Now, before I define natural orbitals, I have to run through this densely populated transparency. I did it on purpose, so I don't have to dwell for a long time on it. Well, just simple thing to understand. We take a wave function of some system, we multiply it by complex conjugate, and we integrate positions and spin coordinates of all the particles but the first one. We multiply it by number of particles. This mathematical entity is called 1 electron reduced density matrix. Chemists are lazy people like everybody else, so we call it 1 matrix, simply. If we do the same thing, but we integrate positions and spin coordinates of particles 3 till n, multiplied by number of pairs of particles, this is so-called 2 electron reduced density matrix or 2 matrix. Now we can look at the diagonal parts of it, which means that we are equating 1 prime with 1. Those are called 1 electron density and 2 electron or pair density, and they can be decomposed into spin components. So there is a spin density corresponding to alpha electrons and to beta electrons. In case of 2 electron density, we have different combinations. Not all the combinations are allowed, in fact, in gamma. So, but this is something that I don't have to tell you about right now. Now, this quantity, which corresponds to probability density of finding 2 electrons exactly at the same point in Cartesian space, is called on-top 2 electron or pair density. And we know that because of antisymmetry of wave function, you cannot have 2 electrons at the same point if they have the same spin. So the only contributions to that on top 2 electron density come from 2 electron or pair densities with electrons with opposite spins. In case of singlet states, everything simplifies. Gamma alpha equals gamma beta, rho alpha equals rho beta, and we'll be using those quantities. Now, important thing to remember that per spin rather than spin summed quantities, or per spin. If you want total quantities, multiply it by 2 or whatever. Okay. Now, here come natural orbitals. You are probably wondering who is this guy. Well, that's a very important person. That's a late Per-Olov Löwdin, who published in 1955 a paper in which he introduced concept of natural orbitals. This paper has been deemed one of the most important papers in quantum chemistry and also in nuclear structure theory, because nuclear physicists use exactly the same concept. And so it was deemed one of the landmark papers, actually the first landmark paper completely theoretical, formal since Schrödinger's. That was deemed in a compendium which was written by Henry Fritz Schaefer. Good old Fritz put 149 landmark papers, and you can see that this paper on natural orbitals is under number 14. Now, just in case of you are wondering what kind of implements Per-Olov has on his head, well, you can ask somebody who's been to Sweden before. But actually, I'm pulling your leg. If this is not a typical Swedish hat, if you are really curious what it is, I will tell you after the talk. So this way, I assure your patience for what I'm talking about here. This one, by the way, was taken during Sunnybell Symposium in 1987. All right, so those natural orbitals are nothing but a Schmidt decomposition of a one matrix, and those numbers are occupation numbers, also ordered non-ascendingly. For singlet states, we also can do decomposition of a Cartesian parts, of a position parts of that. And so in other words, those natural spin orbitals and natural orbitals are eigenfunction of integral kernels given by those one matrices. And occupation numbers are corresponding eigenvalues. Now, because we are talking about fermionic systems, all the occupation numbers are between 0 and 1, and of course they have to sum up to a proper number of electrons, depending whether we are summing over spins n or half n in case of spinless quantities for a singlet state. If we don't have strong electron correlation, so the electrons don't feel each other too strongly, then those natural orbitals are either strongly occupied, which means occupation number is close to 1, or are weakly occupied, which means occupation number is close to 0. And in general, strongly occupied anodes resemble occupied Hartree-Fock or Kohn-Sham orbitals. So you would say, then why do we bother about those natural orbitals? Well, we should bother because all the details, so to speak, electron correlation effects, which have to be taken into account if you want to predict things quantitatively, actually sit in weakly occupied anodes, and they are very, very different from unoccupied Hartree-Fock and Kohn-Sham orbitals. And just to give you an example of that fact, here, coming from a very old paper by Harry Silverstone and others from 79, here you can judge by the quality of those plots, it's a really old paper. Here is an example for a helium atom of different natural orbitals of D type. And if you look at those plots, you can immediately recognize that there is something unusual here, because when you think about hydrogenic orbitals, the higher principal quantum number is, the more diffuse they become. Yeah? If you have e to minus z over n in an exponent, so the higher n, the more diffuse the orbital is, but natural orbitals are not like that. You can actually see that they persistently stick within 0 and roughly 3 atomic units. So we go up to 9.1. There's constantly the same pattern of increasing oscillations, but localization within limited part of the Cartesian space. So that tells us that we really have to use those orbitals instead of Hartree-Fock or Kohn-Sham orbitals if we want, because as I said, they provide the most compact representation of a wave function in terms of one electron quantities. So it tells us that they are so different from those normal Hartree-Fock orbitals that it really makes a lot of difference to use them instead of other types of orbitals. Some properties of natural orbitals, as I said, they are localized. And this observation actually is a key to development of basis sets, those quote-quote atomic orbitals that you should use. And a good example of that is atomic natural orbital basis sets introduced by Almlov and others, and Peter Taylor. and which then evolve into commonly used correlation consistent P, V, T, Z, Q, Z, and so on basis, so which all the quantum chemists know very well. Those natural orbitals exhibit cusps at nuclei, decay exponentially at large distances. An exponent of this asymptotic is this, where I is the first ionization energy. Is the same for all the NOs. Now, so you can see again that they decay at the same rate, while hydrogenic orbitals decay in different rates. They are the rate of decay is inversely proportional to principal quantum number. I picked up randomly really a couple of applications of natural orbitals. There are literally hundreds of them in literature. So you can see there are different things that you can do with natural orbitals. And one of the things for which natural orbitals come very handy is so-called one matrix functional theory, in which a total energy is expressed in terms of one matrix only. Now, this is kind of a new thing in a sense that there is a lot of hope that this theory will replace one day DFT or density functional theory. But there are also some obstacles that I'm not going to talk about today. But when one looks at properties of one matrix, one comes with certain questions. For example, we know that all the occupation numbers have to be between 0 and 1, and the question is, is it possible that some occupation numbers are exactly 1? And the answer is affirmative, yes. There is called pinning states, pinning of states, and it is possible. It is possible that we have infinitely many unoccupied orbitals with occupation number of 0. Yeah, so we could imagine a situation when you have some strongly occupied orbitals with occupation numbers less than 1, then there is a drop, then you have some fractional occupation numbers, and then you go to 0, and that's it. And it can be proven rigorously that this is impossible. You cannot have infinitely many unoccupied natural orbitals, but we can ask another question, which is a much trickier one. Can we have a finite number of occupation numbers vanishing? And the answer is yes, but the evidence for that is only very indirect. So I can show you a particular system and say, this is the thing which has unoccupied natural orbitals. All right, there are some numerical observations that also come from a long time about natural orbitals. There is so-called bunching of nodes that I'm going to skip here, but also universality of NOs pertaining to ground state of a helium atom. For example, I'm using helium atom as a simplest case, so it's easy to see things. So what I have here are radial components of natural orbitals for different angular momenta. So you can see SP, DF, and so on orbitals. And you can see that very quickly they become very similar, right? There's a repetition of the same thing over and over again. That was observed very early in 79, but until a few years ago, nobody had a clue how to explain it. Another thing is there is some regularities observed in occupation numbers, and just to go through it quickly, if you look at occupation numbers for natural orbitals of helium and hydrogen molecule at the equilibrium internuclear distance, it turns out they look very similar. Those occupation numbers look very similar, which is kind of strange because, sure, helium is a united atom limit of a hydrogen molecule, but in a hydrogen molecule at equilibrium distance, this distance between hydrogens is quite large. And so there should be no remnants of helium in it. And it turns out actually are, but we will see later on. And there are also some incorrect observations, like, for example, those numbers which are those natural amplitudes, which are square roots of natural orbitals, absolute values of whose natural absolute values are square roots of occupation numbers of natural orbitals. Some people claim they decay with powers -4 or -5, depending on the situation. Some claim they decay according to with power -4, but with a prefactor, depending on angular momentum and so on. Actually, all those came, again, very early calculations. They came from inaccuracies in those calculations, and one does things correctly. Then one can see, again, we are talking about helium here, because it's easy to see. You can, here what I have is minus natural amplitudes to power 1/4 plotted against the principal quantum number, and you can see it's the same slope for all the L's, and this asymptotic decay law is satisfied to high degree of accuracy already for quite small number n. All right, so we would like now, so that's what has been known until a few years ago, and now we would like to move, I would like to move to what's new in it. Yeah, so can we explain those unexpected regularities in natural orbitals and so on and so on? To do that, we'll first go back to this simple single ground state of 2 electrons coupled to a singlet state. And so again, I just rewrote what I had on the previous transparency. And because of this spectral representation that I already showed you, we can see that natural orbitals, natural amplitudes are solutions of the eigenproblem. And here, wave function plays a role of a kernel of a homogeneous Fredholm equation of a second kind. So if we have any mathematicians here, well, Berge is definitely a mathematician, so something for mathematicians. Oh, okay. Okay. So later I will be discussing some cases of ordinal number, but also combinations of ordinal number within a given angular momentum combined with different values of quantum numbers pertaining to angular momenta or to parity as well. Now, it is known that the wave function the spatial part of wave function that corresponds to 2 electrons has in general this form, and this thing with a bar has continuous first derivatives at the coalescence point, and this is so-called electron-electron cusp condition. And this is going to play a very important role in what you are going to see in a moment. So now let us perform some simple mathematical experiment. Let us assume that we have a wave function which can be written as a product of uncorrelated parts. Yeah. So this is this bar, and the entire wave function would be this product of uncorrelated contributions times the thing that comes with a cusp condition. So if we had a wave function like that, what would happen? Well, we take our Fredholm equation and apply twice to it the Laplacian, and taking into account that applying Laplacian once turns this distance, inter-electron distance, into reciprocal electron distance, and doing it twice turns into Dirac delta. We kill basically the integration here, and we end up with equation like this. Now you could say, well, that's very nice. Yeah, we turn the integral equation into a differential equation of but that works only for this case. Is there a system for which we get a wave function looking like this? Actually, there is. There is this harmonium atom at confinement strength omega equal 1/2. So we end up with so-called biharmonic equation, but this is not a very happy news, actually, because the theory of biharmonic equation is not as developed as a theory of second-order ODEs, ordinary differential equations. So we cannot use any machinery, of standard Liouville theory and so on. So what can we do here? Well, first of all, we should ask the question, what happens in general? Well, it turns out that if those natural orbitals have oscillations and the number of oscillations increases with n, what is missed in this equation decays faster with n than what is left here. Okay, so we can replace this equation with something. Basically, we can rewrite this equation, but for quantities which are asymptotically correct. Yeah, asymptotically correct in a limit of infinite number of oscillations, and that means the occupation numbers decreasing with n, and number of oscillations assumed to increase with n. So that means we are going to get asymptotics of orbitals, natural orbitals for weak occupation regime. So I'm going to rewrite this equation just with just with, where I am actually, yeah, just with tildes. Yeah? So those are approximation to natural orbitals and to occupation numbers. And this quantity is a square of a spatial part of a wave function on top again. And so this quantity, actually it will turn out this is exactly on top to electron density. Well, this is fine, but again, we still have a problem of this biharmonic equation. What can we do with this? Well, since we are talking at highly oscillating functions, the first thing that comes to mind is to use WKB approximation, which is also known in more general terms as iconal approximation. Every time you have a solution which oscillates much more rapidly which corresponds to a potential which varies smoothly comparing to a solution which oscillates very rapidly, you can use it, and that's the case. So we can use WKB approximation because we are looking at highly oscillatory natural orbitals anyway. But that is not going to help us more because in one-dimensional case, namely for spherically symmetric systems, WKB approximation is really useful. But once you have 3 dimensions, things get complicated. You get so-called caustics and so on, and this is a lot of trouble. That's not what we would like to have in quantum chemistry at all. So what can we do? Well, we can play a little trick. We can ask the following question. Can we write a Schrödinger equation that will give us the same WKB approximation, that corresponds to the same WKB approximant, and then asymptotically, this Schrödinger equation will be equivalent to our biharmonic equation. Yeah? So we have biharmonic equation, and we are asking what is a Schrödinger-like equation which shares the same WKB approximate solution. So that's what we can do, and it turns out that's exactly the equation that we have here in case for 2 electrons so far. And here we have our approximations to natural orbitals, occupation numbers. Here we have this on top 2 electron density. So this plays a role of a wave function in this effective zero energy Schrödinger equation, because you can notice that is E equals 0. So we are just at the threshold of unbound states, right? And this thing plays a role of a potential. Now, fine, we have 2 electrons, but can we repeat the same thing for any other system? Sure. If we do it for singlet systems, we can do, and just to go fast, here we play the same trick with one matrix, with this eigenequation, which is equation coming from definition of natural orbitals, and we get tetraharmonic equation, which is even worse than biharmonic equation, but again, we play the same trick, turning into equivalent Schrödinger equation. Now, the key observation here is that one matrix also has a cusp, and in this cusp there is a 2 electron on top. There's a 2 electron density, which turns then into on top density in a final equation. Yeah, so there is this cusp which comes with a 5th power. Believe it or not, the cusp condition for a wave function has been known since 50s of the previous century, works of Cato and others, and this I was able to derive only in 2020. For some reason, that was completely overlooked subject. So when we do, we get this general Schrödinger equation, which is complete, which is generalization of what we got for 2 electrons. So as this thing for 2 electrons is a special case of that. Now I'm going to skip this, but I'm going to show you some interesting things. Yeah? Maybe I should go back for a moment. Yeah? So once again, here, what did I do? Okay, yeah, this plays a role of a potential. This is positive everywhere because it's a density. Yeah, and this is an attractive potential, and the depth of it, or a strength or the depth of this potential becomes greater and greater as occupation number becomes smaller and smaller. So we can ask the following questions. How many bound states are supported by such a potential as a coupling constant goes to infinity? Fortunately for us, there are limits like that known, very famous limits actually in physics. So, for example, here we have one of them. coming from Martin and Tamura. And that gives us number of bound states in a potential like this. And we can invert it now, and we can ask the question, how many, for a given occupation number, how many orbitals we have, how many bound states of that Hamiltonian we have. We revert it now and say, okay, what is a dependence of occupation number on number of those states, on number of the orbitals, yeah? And we get the decay, which is n to 8/3. Yeah? So the occupation numbers for any singlet system decay like n to -8/3 if we order them according to non-ascending occupation numbers. And this is exactly what was derived in much more rigorous way, because the things I'm telling you is kind of hand-waving. Yeah, it's good for quantum chemists, for mathematicians, it's some kind of a heresy, probably. Yeah, but that was derived in a paper running for 20 pages and so on, more or less at the same time by Alex Sobolev in London. Now we can ask another question. What is the number of states in such a potential, but states corresponding to spherically symmetric Hamiltonian, and we have a fixed L and M, the angular momentum numbers. Yeah? So we have fixed N, L, M, and we order orbitals within fixed L and M according to principal number N, like for hydrogenic orbitals, N, L, and M, right? And when we do that, we obtain this asymptotic, which means we have a decay which goes like n to -8. And that's exactly what I showed you before, because I was showing you natural amplitudes that were decaying like n to -4. So when you square it to get occupation numbers, you get n to -8. Now, of course, the question is whether we get correct the prefactor, and in fact it is. And again, we can do one more thing. Actually, we can calculate this limit, and at the limit of n going to infinity, that should be 1. Actually, this can be stripped of those guys here, and we can, because asymptotically is the same thing, and we are left only with kinetic energy operator. And we'll come back to this equation at the very end of this talk, almost very end of this talk. Okay, it is all very nice. We can do the same thing with some other kernels, like a kernel for kinetic energy, but I will skip this. Now we would like to have some numerical verification, yeah? So far we have a prediction that there should be decay of occupation numbers going like n to -8 for spherical systems, and that's exactly what has been seen a long time ago. But what about all this bunching and universality of orbitals? Okay, so I'm going to try to solve this effective Schrödinger equation now. Yeah? In spherical coordinates, because I have system with spherical symmetry. So here is my, so to speak, trial function. I have spherical harmonic. I have a Bessel function. I have something. I have some function, actually, not the Bessel function yet. I have something, and after doing all the algebra, it turns out that this is proportional to a Bessel function, and you have a universal equation for natural orbital of weak occupation, which is valid for any system in 1s state. So any atom, no matter how many electrons, of course, even number, yeah, because we need singlet. So we have this universal equation for approximation to a natural orbital, and this is all consistent provided we have this quantization satisfied, and this is a zero of a Bessel function, but zeros of Bessel functions have no asymptotics. So at the end, we end up with the following equation for occupation numbers, and this is consistent with what I showed you before, and this is consistent with numerics. So this is very nice. Number of nodes, checks, and so on and so on. Now I'm going to skip a lot of tables and equations because this is not important. Now, numerical example. So I just wrote this universal expression for approximation to natural orbital, which is valid at the limit of n going to infinity, right? The occupation number going to 0, infinitely many oscillations, and so on. And our question is, when does it become useful? Do we have to go to like n equal million, or 1,000, or maybe 10 is enough. Yeah? It's not only a matter of asymptotics, but how quickly this asymptotics is reached. And it turns out things are not so bad because I'm going to show you things for n equals 31. Why 31? Well, just pick it randomly from my calculations. So if things are correct, then for any system, if I plot this scaled natural orbital, you can see that I'm scaling it, with some integral and so on and so on. So I can plot everything on a single plot. That should be universal expression given by this, just two Bessel functions basically, and things are controlled by variable tau, which comes from integration involving this on top to electron density. Okay, so let us see whether it works. What I'm going to display for you is with helium, lithium plus, beryllium 2 plus, boron 3 plus, and a harmonium atom. Now, when it comes to those helium isoelectronic series, we would say big deal, yeah? They are all the same potential, it's just dimensional scaling, basically. But harmonium has a very different confining potential, right? So we would expect some deviations here. Now, let's see what we get. Okay, here is the plot. Okay, here's the plot. Well, you see a lot of green here, yeah? And green is a universal function. Yeah, everything else, because you cannot plot things simultaneously, so something is covered by another thing. So all those other guys got covered by this universal function, which was plotted the last. And you see only deviations at very, very large distances, which corresponds to this tau equal 1. That corresponds to r equal infinity. Yeah? So only the tail is not reproduced correctly. Everything else is the same. So those are s orbitals, p orbitals, d orbitals, f orbitals, g orbitals. Same stuff over and over again. One more, H orbitals, L equal 5. Yeah, I don't think I have to go any further because you would get bored very quickly seeing the same thing basically. Now, when I go quickly through it, you can see the only thing that really changes is this, a beginning, yeah, because those are radial Bessel functions. And the rest looks more or less like sine cosine functions. So when I do this, you can see the beginning changes. Yeah, all right. So I can also look at the occupation numbers or natural amplitudes. So I should get a common limit, and here are the asymptotics. This is for helium, different values of angular momentum. This black dot is what one gets from theoretical prediction. You can see that they all go to that limit. We have helium, lithium plus, beryllium 2 plus, boron 3 plus, harmonium. Same story everywhere, yeah? We get asymptotic agreement, as we should. Now, there are some boring tables that I'm going to skip, and I'm going to show some more pictures. Here we have H2 molecule, and this is a radial plot of the integral of this on-top density to 1/8 power, which controls things. So the distance between the origin of coordinate system and some point on this plot is a value of this integral in a given direction. The molecule is oriented along z-axis. So of course for r equals 0, which corresponds to helium, united atom limit, everything is perfectly circular. But you can see that as you go to even to 2 atomic units, which is much greater than equilibrium, in internuclear distance, things are still more or less circular. Yeah, they are not looking very different from the circle. Yeah? A little bit bent maybe, but not that much. And that tells us that contrary to what we would think, there are a lot of remnants of features of helium natural orbitals in natural orbitals of hydrogen molecule. Now that's very strange, yeah, because you would think, we have 2 hydrogens which are apart by 1 atomic unit, roughly. Why should those natural orbitals look like natural orbitals of helium, right? But here is the answer, which is uncovered by this asymptotic analysis. Otherwise, you would never know it. And that also explains why Davidson and Silverstone and so on observed those strange similarities between hydrogen 2 and helium. Now, if you don't believe me, I'm going to show you Again, I will skip this. I'm going to show you some pictures. First of all, I will run very quickly through them back and forth. And it's kind of a game. Try to find the important differences, major differences. So it looks like I'm displaying more or less the same, oops, wrong direction, same shapes over and over again. Yeah? What I have on this is the following, different distances. So here is a distance of 1/10 for atomic unit up to 2. Here is the equilibrium distance. And those things that I'm plotting here are intersections of nodal surfaces of natural orbitals of hydrogen 2 molecule with different distances. Intersections with, let's say, it doesn't matter which plane I pick up, let's say XZ plane. Okay, so in case of a helium, you would just have those things which come from radial nodes, and you would have also those things which come from the fact that those orbitals are multiplied by spherical harmonics. And spherical harmonics have nodes, yeah, in different directions. But as you can see, if I go from one distance to another, the topology more or less remains the same. They look very similar, those pictures. At R equal 2, well, things start looking differently, but until here, and you can look at different symmetries, yeah, those are sigma G orbitals. Now we will have sigma U orbitals, PG, PU, delta G, delta U orbitals, same stuff over and over again. Yeah? So some unusual finding here, which once again is possible only because we were able to turn the Fredholm problem into the effective, asymptotically effective Schrödinger equation. Something for physicists, because I think we have some physics students here, and I'm talking chemistry over here, chemistry. Well, homogeneous electron gas. In homogeneous electron gas, we have something which is called momentum distribution function, which is actually very similar to occupation numbers. Our natural orbitals are plane waves. So it's very easy. Yeah, and you can plug it into this Schrödinger equation, solve it on the back of the envelope, and what you get is this. You get this. Yeah? So it tells us that again there's a decay which goes like k to 8th power, but instead of principal quantum number we have a wave vector number. And what is G0? G0 is so-called on-top value of a per-distribution function of a homogeneous electron gas. Now, I haven't invented America here or something, because this is a well-known Kimball, Yasuhara, Cavazo asymptotics that have been known for many, many years, but it shows that this approach also works for extended systems. And in fact, is much more general than this, because we don't need a homogeneous electron gas. We can have any electron gas. And if we solve Schrödinger equation for natural orbitals, which are not going to be plane waves anymore, we will get estimates for a tail of momentum distribution function. Okay, very quickly, one can get also energy error estimates so the question is, we have finite basis set, yeah, with the so-called truncation error, and we can ask the question how much energy we are losing, gaining actually, because an error is always positive. So what's the error in energy? And there is this celebrated asymptotics of Hill that gave rise to all kinds of extrapolation schemes in quantum chemistry, like scaling with L to minus 3 and so on. Not, of course, with all the due respect to Knight and Hill, well, this is only good for helium-like systems. And people build entire extrapolation techniques based on think this only works for helium system. But it turns out when we do our generalization, we get things that work for arbitrary 1s states of atoms. They even work for arbitrary 1 sigma states of molecules. You get this L to a third power dependence. This I'm going to skip. Now, things sound very good, yeah? Kind of rosy, everything works, but life never works like that. There's always something ugly. Yeah, but what is ugly makes things exciting, of course. Yeah? If everything fit perfectly, there would be no room for further research, and we would be all unemployed, I guess. Yeah? So we're always looking for something new. And it turns out that I started with this assumption, the number of oscillations increases with n. And this is mostly true, or I would say it's almost always true, but there are some single exceptions to it. How do we figure out those exceptions? How can we fish out those exceptions from the sea of normal orbitals? We can do it very simple way. We can look at this ratio that I mentioned before. You remember I had some things around t and I said that we can drop them. So it tends to unity at the limit of n going to infinity. And turns out there are some NOs that have far fewer oscillations than expected from n. N comes from ordering according to non-ascending occupation numbers. So how do we see orbitals like this? Here are natural amplitudes for lithium plus, beryllium 2 plus, boron 3 plus. Those are S-type, and you can see, except for the first one, they're all negative, the so-called normal pattern of natural amplitudes. But if one looks at H minus an ion, well, some ugly guys, sticking out, which have positive natural amplitudes. That's for 2 electron systems, but for many electron systems, we don't have natural amplitudes. We have only we only have occupation numbers. So what can we do? We can plot this ratio, and here you see, for example, this H minus n ion, you can see that this limit of 1 is reached, if I can, this limit of 1, it doesn't look like this, but is reached very quickly. But there are some outliers. And those outliers are those special orbitals that do not work within this theory that I showed you. We can do it also for ground state of helium, of hydrogen 2 molecule with stretch bond. And again, you can see this one guy. There is a lot of noise. Again, we have everything going to 1 very quickly. You can see 40, very close to 1 and so on. But there is one guy that sticks out. What are those things? Those are so-called solitonic natural orbitals. Now, why do I call them solitonic? Well, we have some physicists here, right? What's a typical thing of how do we define solitons? Those are waves that maintain the shape, right? There's this story of some guy who was looking at the wave, which was induced by a boat on some river in England, I forgot which one. And he followed this wave, and this wave was going for miles after miles, maintaining its shape. This was soliton. So there's something similar with those orbitals. Well, here is a very nice trail of solitonic natural orbitals plotted from S-type solitonic natural orbitals for a 2-electron harmonium atom at a quite weak confinement strength. There are few of them, and you can see that they have more or less the same shape. The farther they move away from this nucleus, the more localized they become radially, but they're all of the same shape, more or less, except maybe for the first one. And this is the EKG function, as I call it. Looks like an EKG plot, electrocardiogram. If you ask me what's the analytical form of this function, I will honestly tell you, I have no idea. We don't know how to calculate those guys, so here's an interesting research subject, possibly. And we are almost done. Well, maybe we'll skip take-home message, and instead I will answer your brief questions, because we have only 2 minutes left, it turns out. Thank you for your attention.